Hello. In this video, I shall talk about how we can derive this formula for the sum of a GP using mathematical induction. So in order to do this, recall the steps for mathematical induction. In step 1, we must assume we must prove it for n equals to 1. Okay. In the second step, I must assume that it is true for n equals to k for some value for some k, some number k. And then for step 3, we must then make use of these two, or at least the previous one, and prove the formula for n equals to k plus 1. And once we can do that, we can then conclude that it's true for all n. Okay, so let's start. Now, it's convenient to have the formula here for reference. So let me write it out again. Sn equals to a 1 minus r n over 1 minus r. So step 1, I need to prove it for n equals to 1. So let me write it out. S1 for n equals to 1 is a 1 minus r to the power 1 over 1 minus r, which is, that's just r, right? So 1 minus r over 1 minus r is 1. They cancel. So a then is all we have, right? So those two cancel. So S1 equals to a. So that's what we need to prove. Sum to one term. The sum of one term of the sequence is a, but a is just the first term, right? So the sequence is a, ar, ar squared, and so on until ar to the power n minus 1. So if n is 1, that means we just stop at the first term, right? There's no more. So the sum must then just be a, because there are no other terms. So therefore this is obvious. Alright, it's true because it's obvious. So that's it. That's all we need to say for the proof of this. And in step 2, we need to assume that it's true for n equals to k. Okay. Now, so there isn't actually something to prove for this step. There isn't something to prove for step 2, but it is useful actually. It is useful to actually write out this formula with n substituted by k. So sk is equal to a 1 minus r to the power of k over 1 minus r is what we assume to be true. Okay, we're going to assume this. Assume that it's true. So for now, we have not actually proved this formula, but let's just pretend that it's true. And in step 3, I need to prove it for n equals to k plus 1. I need to prove sk plus 1, prove that sk plus 1 is equal to a 1 minus r k plus 1 over 1 minus r. So in order to do this, okay, we can try starting from the left hand side or the right hand side. Okay, let me try starting from the left hand side. So as the left hand side is s of k plus 1. Now s of k plus 1 is the sum to the k plus 1 term, sum of k plus 1 terms. In order to prove it, it helps to remember that we are supposed to make use of what we already know. In this case, this. But that's not the only, this is not the only thing that we know. There are other things like the basic meanings of the sequence. So, for example, as n is supposed to be ar squared plus dot 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 until ar to the power of n minus 1. So that's the basic meaning, basic sum that we want to prove. So from this and this, we have to try and relate it to what we see here in this equation that we would want to prove. And the way is to think about, in this case, is to think about the relation between sk plus 1 and sk. Sk means we sum up to the k term. Sk plus 1 means we sum up to the k plus 1 term. So in other words, this sum contains one term more than this sum. And that extra term is the k plus 1 term. So the sum to the k plus 1 term is therefore, I can think of it as the sum to k terms plus the k plus 1 term, which is ar to the power of k. Remember that the power here must be 1 less than the ordering of the term. So in this way, I can relate k plus 1 to sk plus 1 to sk. Now, but why would I want to do this? Well, usually I want to relate it to what we know in order to hopefully make use of what we know to prove what we want. It may or may not work, but in this case I know it does. So let's carry on. So sk is actually this. So let me now substitute this into sk. A 1 minus rk over 1 minus r plus a r to the power of k. Right, so I have this now. Now remember what we are aiming towards. We are aiming to show that the left hand side is equal to the right hand side. So what I need to do now is to somehow show that this is the same as this left hand side. Now it's kind of looking promising because you see now I have all the a's and r's and the k's here. Okay, and I also have a, r's and k's here. So maybe I can somehow rearrange this so that it looks like this. So how can I do it? Well, the usual thing, well, one thing that might help is to always look at the thing that we want to prove. Okay, and see how we can rearrange this to make it look more like this. So if you look at this, it looks like there's only one fraction here, this over this, and no other terms. But in this case, I have two terms. Okay, but I have this denominator that happens to look the same as this. So what I could try is to perhaps combine those two terms into a single fraction. Okay, and also notice that I have a here and a here as a common factor. So if I factor out the a, and I put this and this under this over the same denominator, then this part is just the same, 1 minus rk. That part would become this times this. Okay, so it becomes 1 minus r times rk. Okay, so look at this again. Not quite the same yet, but maybe if I can simplify this, it might help. So let me try that. 1 minus r. 1 minus rk. Okay, I'll open up the bracket, remove the brackets. So 1 times rk is rk minus r times rk is minus rk plus 1. Okay, so what we have now is this expression. Now there's one thing I can simplify right away. See that there's a minus rk here and a rk here. So those two cancel. And now if you compare this with this, you can see that they are actually the same. So therefore this is equal to the right hand side, and we have just proven it. We've just proven that this is true. So now that we've proved that this is true, we can then conclude. We can then conclude by saying that by mathematical induction, since okay, maybe I'll write this out. It's good to know this more clearly. Okay, so we have proven it for 1. Okay, don't forget, we have already proven it for 1. For n equals to 1, we have shown that it's true. And when we assume that it's true for n equals to k, I've just proven it for n equals to k plus 1. So then we conclude by saying this. Therefore, since it is true for n equals to 1, and since if it is true for n equals to k, it is true for n equals to k plus 1. Therefore, it must be true for all n. Okay, so you see how it works. It's true for n equals to 1. Then the next sentence proves that if it's true for n equals to any particular value of k, then it's always true for the next value of k. And the reason why we can conclude this is because we can apply the second sentence here to the first sentence. So if let's say k is 1, then according to the second sentence, if it's true for n equals to 1, it must be true for n equals to 1 plus 1, which is 2. Then we can say that, okay, so the second sentence shows that it is true for n equals to 2. But if it's true for n is equal to 2, then the second sentence must show that it is true for 2 plus 1. So it's true for n equals to 3. And you can just keep repeating this, just apply the second sentence over and over again. When you show that it's true for n equals to 2, the second sentence tells us that it's true for n equals to 3. True for n equals to 3 must be true for n equals to 4. And it just keeps going on and on forever. So that's why we can say, therefore it must be true for all n. And that's what mathematical induction is all about.